Okay, so welcome everyone to the final meeting for the Integrable Probability Seminar this semester. And so Jiaoyang Huang from NYU will be ending this with a talk about height fluctuations of random Lozenge tilings through non-intersecting random walks. So take it away.
Yeah, I want to thank you for the invitation. As Andrew mentioned, the talk I will give is on the height function of random Lorentz tilings. So I'm sure most of you here are familiar with this random Lorentz tiling, but let me still just quickly go through the background and the setting. So for the Lorentz tiling, you basically fix a domain and tile it with those three types of Lorentz. The random Lorentz tiling is just this uniform probability measure on the set of all the possible Lorentz tilings of this given domain, like this hexagonal domain. And you can also think this like just a pile of a bunch of those 3D boxes. So this is also called the box partition. If you think it this way, then this gives you a 3D surface. So you can also think this random Lorentz tiling as an example of those random surfaces. So here are some more simulations of the Lorentz tiling, as you can see from this simulation. And for a given domain, if you look at close to the color of those domain, usually you can only see one type of Lorentz. So these domains are called the frozen region. Only one type of Lorentz are there, like also this color or this color. And close to the center of the domain, you can see all three types of those Lorentzes. So this region are called the liquid region. It contains all three types of the Lorentz. At the boundary curve, which separates the frozen region and the liquid region, it's called the Arctic curve. And for my talk, I will mainly treat the Lorentz tiling as this non-intersecting Bernoulli walk. So to identify a Lorentz tiling with a Bernoulli walk, we need to do a little bit this affine transform, just to change the lattice in this way. So the sides of the lattice is either horizontal or vertical, or those 45-degree direction. Then in this way, the Lorentzes will become those square, those blue Lorentz, and those red and the green ones. And each Lorentz just consists of two of those small triangles. And if you think it this way, then if you ignore those red Lorentzes, like you get this picture. As you can see, those blue Lorentz and the green Lorentz, they form paths. Just this is the first path, this is the second path, and this is the third path. And if you think this is a particle system, you start with those four particles. And blue Lorentz means you just stay. Oh, you think this horizontal is a space dimension, and the vertical is a time. So if you start with four particles, the blue means you stay, and the green means you jump one step to the right. And then you get this new configuration, and blue is stay, and the green is jump to the right. And then at this moment, you add another four particles. If you think it's this way, a particle is either stay or jump to the right. So this is a Bernoulli walk. And also you need to make sure at any one side, there's at most one particle. So those particles, they do not overlap. That's why it's the non-intersecting Bernoulli walk. And as mentioned, for this Lorentz tiling, you can think it's a surface. So to make the surface compatible with the non-intersecting Bernoulli walk, I will take the left-hand side to the bottom, and right-hand side at the top. And since those red Lorentz, they are flat, so this is of height 0. Those are of height 1. Those are of height 2, and keep going. You can think it's simply for the first pass, everything on the left of the first pass, it's height 0. Between the first pass and second pass, it's height 1. And between second pass and third pass, it's height 2. And we denote the height function by h, the capital H. And another notion I need is this local density triple. So for any given height function h, we introduce the local density triple, which is basically you pick any point xt and look at its small neighborhood, and then you compute the density of those three types of Lozenge. You get those three number p, which are the densities for those three types of Lozenge. The sum is 1. You can also directly compute this local density triple from the height function. Like if you take the derivative with respect to x, which is a horizontal direction, as you can see, if it's a blue Lozenge, the derivative is 1. Or if it's a green Lozenge, the derivative is also 1. If it's red Lozenge, the derivative is 0. So the height function, the derivative with x is the density for the green Lozenge and the density with a blue and the green Lozenge. And it's also 1 minus the density for the red Lozenge. Similarly, you can take the derivative with respect to t. And for that one, if it's red, the derivative is 0. It's blue, the derivative is also 0. If it's green, the derivative is minus 1. So it's minus the density for the green Lozenge. And the first theorem I will explain is this theorem obtained by Cohen, Kenyon, and Prop about 20 years ago. So their results give a large deviation result for the Lozenge tiling. So for any p, which is a domain in the plane, and we rescale it by a factor n. Because here we use the Lozenge, each side is of length 1. You can also think equivalently, you can just make this lattice smaller of size 1 over n. So then you get this height function for the random Lozenge tiling. Then there results is if the height function, you normalize it by a factor n. This guy is close to some given surface h. The number of such Lozenge tiling is approximately given by e to the n squared times this rate function. And the rate function is the integral on the domain P with the surface tension sigma. And the sigma, the expression is given here. So it's defined at every point given those three types of, those three local density. It's kind of complicated, but the graph of the sigma is here. As you can see, it's strictly convex. It's defined on this this triangle domain. This is x derivative with respect to x. This axis is h derivative with respect to t. So it's strictly convex inside this triangle, but it's linear on the boundary. So it's not strictly convex on the boundary. Then if with this large deviation result, if you want to know the limit shape, you just take the supremum on the right-hand side. You get this h star. H star is the supremum of the rate function. H star is the argmax for this guy. And then you can conclude from this large deviation result, the height function normalized by n converges to this h star. And from the PDE knowledge, we know if the surface tension sigma, if it's strictly convex, then we will have h star, it's smooth. But for this surface tension, it's only convex inside this triangle, but it's not strictly convex on the boundary. That's why we get this h star. You have the frozen region at the liquid region. Oh, one thing, even if you are given the domain P, h star is given by this variational problem, it's not that easy to directly solve this h star. Even if you write down the Euler-Lagrangian equation for h star, it's not that easy to solve it. And to get the limit shape, Cohen and Okounkov, they introduced this quantity called the complex slope. So for any local density triple, those three p's at some point xt, you associate it with a complex slope, which is a number. Because my notion is slightly different from their notion, because I take the left side to be the bottom right side to be the top. So my complex slope is in the lower half complex plane. So basically, you take this triangle with the vertices at -1, 0, at f, and those three angles, they parameterize those local density. So this angle is pi times the density for the green and orange, and this is pi times the density for the red and orange. And in this way, if you have the liquid region, inside the liquid region, you have all types of Lorentz, so those densities are positive. So F must be in the lower half plane. But if you are close to those colors, like if this color, you only have the blue Lorentz, which means this local density will be 1, 0, 0. So F, this angle should be pi, and the other angles are 0. So F must be between -1 and 0. So on this part of the Arctic curve, F is between -1 and 0. And close to this one, you only have the red Lorentz. So this will be pi. So F, and those two angles are 0. So F is in the positive axis. So this on this boundary of Arctic curve, F is between 0 and infinite. And especially then you can determine the values on the boundary on the Arctic curve. On the Arctic curve, the complex slope, they are real. And in fact, you can directly get it from this picture. It's you can compute it out by the slope of the tangent for the Arctic curve. And especially on those points, the Arctic curve is tangent to the boundary, like this point, F must be 0. Because F is -1 to 0 on this curve, at the 0 to infinite on this curve. So F must be 0 here, and similarly F is infinite here. So in this way, given the H star and the local density triple and the complex slope, those three objects, one determines the other. And the results by Kenyon and Okounkov they get is, if you think in terms of this complex slope, then it satisfies this complex Berger's equation. So it's a ft, the time derivative, plus ft derivative with respect to x, and ft over ft plus 1 equals 0. This is exactly the same as the Berger's equation, except that ft can take the complex value. So it's called the complex Berger's equation. For the complex Berger's equation, you can solve it the same as the Berger's equation by the characteristic method. Just define the characteristic by xt, time derivative is just this quantity, ftxt over ftxt plus 1. Then this becomes ftxt, the time derivative is 0. So if you know f0, you can use this to solve ft. But the only problem here is if you define the characteristics this way, because ft takes complex value, so the characteristics will go to the complex plane. So you need to extend the complex slope to the complex plane. And in this way, Kenyon and Okounkov, they proved if the polygonal domain P, for any given polygonal domain P, there exists an algebraic function of two variables, this Q, such that f, x, and t, they satisfy this equation Qf, x minus t, f over f plus 1 equals 0. If you take the derivative, if you think this is a function of f, x, and t, use the implicit function theorem, f is a function of x and t. Then you can take derivative with respect to x on both sides. You get the first equation. And take derivative with respect to t. Oh, with respect to t, you get this one. With respect to x, you get the second one. And then you eliminate the q derivatives. You get back to this complex Berger's equation. So in other words, given any this q, the solution fxt, it gives a solution for the complex Berger's equation. But the hard part for this theorem is they actually prove given any polygonal domain P and the limit shape, the corresponding complex slope, there exists such Q. And because Q is algebraic, you can think this Q, it defines a Riemann surface. And in the paper, Kenyon and Okounkov, they made this conjecture. You can think this Riemann surface, it gives a map from the liquid region to the Riemann surface Q. Use this map from xt to f, x minus t times f over f plus 1. And you can directly check to see this map actually it's injection, bijection to its image. So in this way, this map, the complex structure on the Riemann surface Q, it induced a complex structure on the liquid region. And their conjecture basis is in the liquid region, the height function. Oh, I want to emphasize a little bit on the frozen region, the height function is linear. So it's so it doesn't fluctuate at all. So if you ask for the fluctuation, you should it's only interesting inside the liquid region. So the conjecture is h subtract its mean and rescale by square root pi. You get a Gaussian free field on the liquid region. And it's a Gaussian free field with the zero boundary condition, the Dirichlet boundary condition. But you don't use the complex structure just from the C. You use the complex structure induced by this Riemann surface Q. So let me just explain this a little bit more. So usually when we consider the Gaussian free field phi on some complex domain D with a zero boundary condition, it's a random distribution. We can pair it with only two functions on the domain D, G and H. Then phi G and phi H, they are Gaussian random variables with the expectation given by the integral on the domain D, G times the Laplace inverse times H dx dy. So informally, if we, although phi is not a function, informally see if we think it's just a Gaussian vector, you can think this is like a discrete Gaussian free field. Then its covariance is given by the inverse of the Laplacian. So if we write down the density of this vector, we will have the density of the Gaussian free fields just given by the density of Gaussian. So it's e to the 1/2 times the integral of phi, Laplacian phi, dx dy. Then you integrate by part, get the gradient of phi squared dx dy. And if you want to emphasize the complex structure, then you can write dx dy will give you half dz bar. And the gradient of phi squared will give you d phi dz times d phi dz bar. Then you have the density, something like this. And for the sitting in that conjecture, the Gaussian free field, you didn't directly use the complex structure dz from the complex plane. You use the complex structure from the Riemann surface Q. So you can think this liquid region has a map to the Riemann surface Q. Then if you just simply project to the first coordinate, then this simply it's the map from the liquid region. Use the complex, nope, it maps to the domain D. But this is not very rigorous because F may not be a bijection. But you can roughly think it this way. Then the Gaussian free field on the liquid region is just a pullback of the Gaussian free field on D using this map F. So in other words, take only two functions G and H on the domain D. The Gaussian free field, then you pull it back, get a function G composed with F and H composed of F. And the phi act on them, the two are Gaussian variables, and the covariance is given by integral of G, Laplace inverse H dx dy. So as in the last slides, if we directly write down the density of phi, the density is given by this guy, e to the pi I times the integral on the liquid region, d phi df, d phi df bar, and df bar. So here you just simply think phi as a function of f. So everything is the same as this guy, except we just replace the complex structure dz by the complex structure of f, replace just z by f. So this is a Gaussian free field in their conjecture. And there is a very nice heuristic given by Van Dien. You can find it in his lecture notes. I think soon it will become a book. So the heuristic goes like this. So according to the large deviation result of Cohen, Ken, and Prop, we roughly have the height function normalized by n. It's close to some surface edge. It's roughly given by e to the n squared times this rate function. Now imagine we have a probability density on the set of the surface's edge, which is exactly given by the first term, the rate function. So we have probability h, it's proportional to e to the n squared times this surface tension. And we know h star, the limit shape, is the maximizer of this guy. So if we want to study its fluctuation, we can define, just expand around h star. So h equals h star plus delta h over n. And then we can plug in this back to this density. Because h star is the maximizer, so the zeroth order term and the first order term, when you plug in and do the Taylor expand, they all disappear. So only thing left, the leading term will be the second order term. And then you will have 1 over n squared times cancels with this n squared. And after some algebra, you will get this density, it becomes a density of this delta h. You get p delta h is proportional to pi I times the integral of d delta h df, d delta h df bar, and df bar. This is exactly the density for the Gaussian free field in last slides. And so, but the problem for this heuristic is if the only thing which is not rigorous is here. So here, in the large deviation, the error term is of little o n squared. But in order to see the Gaussian fluctuation, you need the error to be of little 1. So really, to improve this error from little n squared to little 1, it's pretty hard. And more importantly, like in many other systems, actually, there are some other errors. Although the first order error is given by n squared, it turns out there are some other errors of order n, but they do not affect the fluctuation, as you will soon see. And my result is a proof of this conjecture for a family of domains P. So far, any question? So let me just quickly go through the previous, some previous results about this conjecture, tell you what we know so far. The first, for many domains like this triangle domain, as you can see from this simulation, it does not have a frozen region. It only have liquid region. So for domain of this, we know that the fluctuation converges to the Gaussian free field. And there are a lot of recent progress in this direction developed by those people. And the second domains we know is like for this trapezoid domain. You start with the trapezoids and remove a lot of wedges on the bottom. So for this is done by Petrov. And for this one, this is equivalent to the Guilford pattern. You can write down like the partition function explicitly and you can analyze it. And the third class of domains are ones like this. It's a hexagonal domain with many holes. Domains like this, which is not simply collected, and Buffetto-Fagorin proved that the height function fluctuation still converges to the Gaussian free field using the Schur generating function. And the domains I can prove are domains like this. It's a polygonal domain which has exactly one horizontal upper boundary edges, like the trapezoid domain. It has only one horizontal upper boundary edges. Other horizontal edges are the bottom edges. Also, you can consider domains like those two. You can have a pretty general left and right boundaries. But this does not include domains like this guy. You have two upper boundary edges. And for those boundaries, we prove the height function subtract its mean and times square root pi converges to the Gaussian free field.
So can I ask a question?
Yeah.
You go.
Okay. So in the language of Bernoulli random walkers, you're assuming that your random walkers are starting from packed initial configuration, but they're allowed to have a bottom and lower boundary for the trajectories, which is fairly arbitrary. Is that correct?
Yeah. If you rotate it, you can think you start with this packed configuration as you just run the Bernoulli line-intersecting Bernoulli random walk. You can have a pretty general. You can have some particles stop here, some stop here at a pretty general left and right boundary.
Okay, so it's Bernoulli random walkers with particles being killed. Is that what's happening?
Oh, you can think this path is just some paths just stop here, some paths stop here, and some paths stop here.
Oh, okay. You can just project to your path space and ignore parts of it, and you just get the GFF because it's stable under projections.
Yeah, you can change the number of particles along this process.
But there's no way of forcing them all to be at given locations at a fixed time, right? You're conditioning on different times, like in this middle picture, right? Mm-hmm. Or is there a way to condition them all at the bottom to be in certain locations and get the same picture?
So can you repeat? Sorry, what's
well, like say the leftmost particle, right? The one that starts at the left of the red region, right? So eventually he needs to end at the left of that region there, right? So is there a way to draw a picture which would result in him needing to end there, but also then continue on? You know, could you draw a boundary condition?
You mean here what? Yeah. So you can.
I think the answer is no, right?
So sorry, what do you mean? Ask it to continue?
Well, I want a picture that looks like the first picture, one where all of the horizontals are on the bottom.
Oh yeah, I think you can do that. You can have everything on the bottom.
Oh, okay. Oh, so you can.
Yeah. So also you can like it's the same as the first picture, but they end at a different time.
So is this a sure process then?
Yeah, you mean like the first picture, but those three bottom, those height, they are of different height.
Okay, let me. Why don't you go on? Sorry.
Okay, maybe after the proof, I will explain why I get this condition. Then that's maybe I can explain at that time. So yeah, let me just explain the proof ingredients. So here we take a dynamical approach to study the random Lorentz tilings of those polygonal domain. So we identify them with the non-intersecting Bernoulli random walk. So for this picture, yeah, it's basically it's just this. You can have a particle start from different location, but all of them end at this at time capital T. You start from time 0 and everything end at capital T. So if you look at the time slice at the time t, we denote the particle configuration by x1t, x2t, and xmt. They are all on the lattice of z over n. Mt is the number of particles at time t. And this is uniquely determined by the polygonal domain P. And non-intersecting just means those xi, they are at a different location. So those are the strict inequality. And we define the function capital NT to be the number of those non-intersecting Bernoulli walks stay inside the domain P and starting from the particle configuration X at the time T. So this NT is the number of such non-intersecting Bernoulli random walk. And if this configuration X, if two particles, they overlap, we simply set this NT to be 0. Or if the configuration is outside this domain P, we also set this NT to be 0. Then you can can get this NT is satisfy this recursion, which is a discrete heat equation. So NT, at the time t, you start from the configuration x, and the number of the non-intersecting Bernoulli work will be equal to the sum over the vector E, which is a 0, 1 vector. So which means that EI equals 1 means the particle jump to, the ith particle jump to right. And if EI equals 0, which means the ith particle is just stay. So this equals sum of at the next time step, n, t plus 1 over n, at the new configuration x plus e over n. So you have this recursion. And to directly solve this recursion, it's hard because of these boundary conditions. You want to make sure the particles, they don't overlap. So if in the new, after the jump for the new configuration, two particles, they overlap, this term is 0. Or after one step, those particles, they leave the region P, this term is also 0. Because of those boundary conditions, it makes to solve this equation hard. Otherwise, you can simply solve it by the discrete Fourier transform. And you can also think this NTX as a certain number of Lorentz tiling. You can just take the region P as a restrict and only look at the parts from small t to capital T. At the bottom boundary is given by the configuration X. Then this NTX, it just counts the number of Lorentz tiling for this new domain, with bottom given by the particle configuration X.
So what happens if the number of particles changes from level to level? Like that's possible, right?
Yeah. So like here, the change only happens if there's a horizontal boundary edge, right? Otherwise, the number of particles will not change.
But in your recurrence formulas, what changes?
Oh, in this recursion, if so, basically like at this time,
right?
Then you will have NTX. It's still the same, because at any one time slice, like at this time slice, you actually it corresponds to the particle configuration. You can think it's a 4-particle configuration. You can also think it's an 8-particle configuration, right? Just equivalent to those two configurations. Because the particle added, those 4 particle added, it's only depend on the domain P. It's prefixed. It's independent of the line-intersecting Bernoulli random walk.
So is there a way to kind of deterministically extend the domain so that you kind of start with the same number of particles to begin with?
No, I don't think you can extend the domain. It has to be at this moment. You start a for
okay, so your function n that you currently have, actually it implicitly depends on the domain itself.
Yeah, it depends on the whole domain.
Okay, I understand. Thank you.
Okay, thank you for this classifying question. And yeah, it's essentially counts the Lorentz tiling with some given bottom boundary. And use this NT, we can define this non-intersecting Bernoulli random walk with the transition probability given by the ratio of the partition function. Basically, at time t, start with configuration x. At the next time, you're at x plus e over n. The probability is just the x plus e over n over ntx. So you can see for this non-intersecting Bernoulli random walk, it's essentially equivalent to the uniform random Lorentz tiling. So to understand the random Lorentz tiling, it's the same to understand this Bernoulli random walk with this transition probability. Yeah. So, but here still we do not know this NTX. We cannot directly analyze this transition probability. But if you think from that large deviation results, we know that given a domain P, the number of Lorentz tiling is roughly given by e to the n square times the rate function. And because this NTX, it also counts a certain number of Lorentz. So we will also roughly have it equals e to the n square times the the rate function for this region, which corresponds to P, restrict from little t to capital T. At the bottom, it's given by this configuration X. So NTX should be roughly given by this guy. So if you believe it, then we can make this guess. Basically, NTX, you just guess it's given by the rate function e to the n squared WT. It's this term times some correction term, which is ETX. So if you just guess this way, you will think that this correction term it should be much smaller than the leading term. And then in this way, we can plug in this back to this non-intersecting Bernoulli random walk. And then we will have the ratio of the correction term and also the difference for the leading term, which is e to the n squared, WT plus 1 over n, subtract the WT. And for WT, we have this explicit formula. So we can compute this term pretty precisely and just by a Taylor expand. The Taylor expand for time, which gives something which is independent of E. We just denote it by 1 over ZTX. A Taylor expands for each of those xi. Then after some algebra, then you can rewrite it as in this way. It's given by the ratio of the Vandermonde determinant. The Vandermonde of the new configuration at x plus e over n, and the Vandermonde at the configuration x, and times the drift term, it's gt to the ei. And the drift term is given by this formula, it's log of gt at xi, given by n times this function wt, derivative with respect to xi. Subtract the Hilbert transform of rho. Rho is the empirical measure for the x. So you can just think it's this derivative with respect to this xi. Just by Taylor expand this term, you have the derivative with respect to xi. And the subtract the Hilbert transform correspond to the ratio of the Vandermonde. Because for the Vandermonde, after you take log and take derivative with respect to xi, you get the Hilbert transform. So you get roughly this expression. It's not very precise. There are many other terms because of this discretization. I just use this tilt location, but you can analyze still this way. The idea is the same, although the real formula is more complicated than this one. Then we have for the recursion of this NTX, it's essentially just says this is the transition probability. So you sum over all the E, this equals 1. Then you can use it to write down the recursion for this ETX. So in this way, you move ETX to the left-hand side. ETX will be this guy sum over all the vector E, it equals 1. So it's sum over E, you get ETX. So you get this recursion for ETX. So for this recursion, we can solve it by introducing this new non-intersecting Bernoulli random walk, which is x tilde t from x at time t to x plus e over n at time t plus 1 over n. Then you basically, I just copy this part. It's the transition probability is given by the ratio of Vandermonde times the drift term. And using this non-intersecting Bernoulli walk, this recursion can be solved using Feynman-Kant's formula. It's basically ETX. It equals, you start this non-intersecting Bernoulli random walk from time t at the configuration x. And then you run this non-intersecting Bernoulli random walk. And I want to see a little bit, those two partition functions, they are different. This partition function is chosen such that this is the transition probability. So it equals the ratio of those two partition functions at time s. S is between t and the capital T. So if there's no this correction, if there's no this correction term, then ZT will be ZT tilde. So this correction term is just a collection of all the ratio of those partition function. And this E capital T corresponds to the boundary term in our setting, it's just 1. So I want to see, like, before I mentioned it's hard to directly solve the recursion for NTX because of those boundary conditions. The particles cannot overlap and the particles will stay inside the domain P. The advantage to use this recursion is for this new non-intersecting Bernoulli random walk, all those boundary conditions are encoded by the transition probability. So you don't need to worry about the boundary conditions. So let me be a little bit more precise. So see if you start from
can I ask a question? So the X tilde is not, in fact, Bernoulli random walkers that are conditioned to not intersect by some Dubage transform. Instead, it's something that whose trajectories are like those of avoiding random walks, but have some weird transition probabilities.
Yeah, I think you can think it's just have some drift term GT. Like for the standard non-intersecting Bernoulli random walk with the drift beta, this will be like something like a beta to the EI times 1 minus beta to the.
But my point is, it's not that. It's more complicated somehow.
Yeah, it's more general because those drifts depend on time at the location.
But does it not also depend somehow on your polygonal domain, or is this?
Yeah. We fix the polygonal domain. It depends on the polygonal domain.
Right. So it's not somehow freely evolving random walkers. There's some kind of overarching dependence on the domain that is happening.
No, it depends on the domain P. So you will see it in fact encodes all the information of the domain P.
Okay.
If you start from at time T, it has a configuration X. After one step, you add the configuration X plus E over N. Because of this Vandermonde determinant, if for this new configuration, 2 particles, they overlap, then this way becomes 0. So the transition probability is 0. So it makes sure after one jump, particles are non-intersecting. So another boundary condition is you want to stay inside the polygonal domain. So here I didn't give you the formula for GT, but if you estimate it, you will see it actually encodes the boundary condition of the polygonal domain P. If the left boundary is this 45-degree boundary, the GT, it has a pole here at the boundary point. It equals infinite. If the right boundary is vertical, GT has a 0 here, which means the particle, if it's next to the left boundary, and the left boundary is this 45-degree boundary, because of this drift, the particle has to jump to the right for next step. So which makes sure the particles stay inside the boundary. And if there's a particle close to the right boundary, which is this vertical one, then the next step, if EI equals 1, then this term is 0. The probability is 0. So EI has to be 0. So which means that the particle cannot jump. So it will also stay inside the polygonal domain. So the advantage for this one is it encodes all the boundary condition and staying non-intersecting. So when you analyze this dynamic, you don't need to think about those boundary conditions.
Can I ask a question though?
Yeah, sure.
So I'm still somehow wondering about, so basically you have several times kind of macroscopically in which a batch of new particles is entering your system, right?
Yeah.
So is it the case that you're kind of sequentially solving in each slab, kind of where the number of particles is fixed, you're solving this sort of recurrence equation, kind of starting from the top and then, get something for the next slice where the last batch entered and then recursively solve. Is that what's happening?
Yeah, I think essentially you can do that because it's everything is about this recursion. If you know it's at like some time t1, you can start from the t1 to solve it. So when I need to cut, you can cut those domain whenever there's the horizontal boundary and solve them just recursively.
But is that what you're doing, or is that just doable?
Oh, actually, you can also put those that will give some extra term in this Feynman-Katz formula. You can just put it here, directly solve them at the same time.
Okay, so somehow the state space of your interacting particle system can accommodate having different number of particles for different levels. Somehow.
Yeah, but it's essentially the same as you solve them at like finite number of times. It's as long as it's finite number, the error won't accumulate too much, so you can do it.
Well, you're assuming you have a polygonal domain, so there are only finitely many places where, right? So okay, thank you.
Yes, so you can have the horizontal edge at a different time. Then to analyze this non-intersecting Bernoulli random walk, the tool we use is the loop equation. So loop equation, it's important tool to study the interacting particle systems. So they were introduced by Johansen to study those beta ensemble. So I'm sure all of you have seen this beta ensemble at some place. So if V is it's a n-particle system on the real line, and the interacting between two particles, lambda I and lambda j, is given by this lambda I minus lambda j to the beta. And you have weights for each lambda I. If the weight is quadratic, then beta equals 1 correspond to the eigenvalues of GOE, beta equals 2 correspond to the GUE, and beta equals 4 correspond to the Gaussian symplectic ensemble. It gives the semicircle distribution from -2 to 2. And if you want to study this particle system, usually we just encode it by the empirical particle density d mu n. So which is 1 over n sum of delta lambda I. So we can encode it by the Stieltjes transform, which is mn, which is the integral of d mu n over z minus lambda. So which is 1 over n sum over 1 over z minus lambda I explicitly. So all the information of the particle density is encoded by the Stieltjes transform. Like for the linear statistics with the analytic test function, so which is the sum of f lambda I, which is also n times f times d mu n, which is, you can write it as this contour integral with respect to the Stieltjes transform. So, this contour enclose all the particles. So in this way, to understand the law of large number at the central limit theorem of the measure, you only need to understand the law of large number at central limit theorem for this Mn, the Stieltjes transform at a different z. And the loop equation is just some equations about the Stieltjes transform, or a family of equations about the expectation for the Stieltjes transform. Like for the first order loop equation, it gives something like this. It essentially follows from just by integration by parts. It gives the expectation of mn square, subtract 2v prime over beta times the expectation of the Stieltjes transform plus something analytic. Explicitly, it's this guy. If v is analytic, as you can see, the pole it cancels, so this guy is analytic, equals some higher order error term, which is 1 over n order. And the limits, you get the limit equation, which is this guy is the expectation of mn converges to mv. Then you get mv squared subtract 2 times v prime over beta mv plus something analytic equals 0. And the Stieltjes transform, you know it looks something like this. At infinite, it behaves like 1 over z, and it only has residue on the real axis. So the limit mv, it also only have the residue on the real axis. At infinite, it behaves like 1 over z. If it's one card, actually this equation, it uniquely determines this mv. Although you don't know this analytic part, but you only know it's analytic, still this uniquely determine mv. So in this way, you get the expectation of Stieltjes transform, the first order term. And after you take the difference, you can use it to get the higher order term. So loop equation, usually it's something like this, has this flavor. You have some quantity, which is analytic. Although you don't need to know explicit the analytic term, you can still solve it. And this is for the continuous system. For the Lozenge tiling, we have it's the discrete system. We also have those discrete beta ensemble. Here it's only for beta equals 2. It's essentially the same as the continuous beta ensemble. Only the density is essentially the same, except here xi, they are on the lattice, the over n. And we will get this kind of discrete beta ensemble, like for the one-time slice of the Lozenge tiling, or one-time slice of those domino tiling for this rectangular domain. For those discrete beta ensemble, we also have the loop equation, the discrete loop equation. It's proven by Borodinko, and Gianni, originated in some physics work by Nekrasov. They show their result is more general than this one. They can actually take beta to be anything, not necessarily beta to be 2. They assume that the weight, like in the beta equals 2 setting, it's if the weight satisfies this one, Wx over Wx minus 1 over n equals phi plus over phi minus. At phi plus, phi minus, they are analytic. Then you have this quantity, it's analytic. The phi minus times some expectation plus phi plus some expectation. As before taking expectation, it will have poles at this like xi at xi plus 1 over n. But after taking expectation, the poles, they just cancel out. And for this one, if you do some Taylor expand, you get something like sum over 1 over n, 1 over z minus xi. You get something like the Stieltjes transform. So you can analyze it to get the Stieltjes transform for this particle system. And analyze it, gets the law of large number as central limit theorem. But for our setting, we do not explicitly have the density, but we have this transition probability. If our transition probability is in this form at time x, next time at x plus e over n, it's given by the ratio of the Vandermonde times the drift term, it's a phi plus to the ei times phi minus to the 1 minus ei. And if ei is 1, you jump to the right for 1 step. Then you just take the phi plus. If you stay, ei is 0, you take the weight of phi minus. So for this drifted non-intersecting Bernoulli random walk, we have the loop equation. I just call it the dynamic version of the loop equation. It's still some quantity. The expectation is 0. It consists of 2 parts, phi plus times something plus something times phi minus. So as you can, the same as those previous loop equations, you can analyze this loop equation to get the information about this transition probability. And if you denote the Stieltjes transform for configuration x by just 1 over n, sum over 1 over z minus xi, and the configuration at after 1 jump at x plus e over n, the Stieltjes transform by 1 over n, sum over 1 over z minus xi minus ei over n. So here the randomness is at those ei. And then analyze this dynamical loop equation, you can get the change for the Stieltjes transform. So mt plus 1 over n, subtract mt, you get it has a random part given by 1 over n times square root n, a martingale term, plus 1 over n times a deterministic shift. So because our time is of macroscopic time correspond to ON steps. So as you can see, after ON steps, those deterministic shifts, they accumulate, then gets the MT, the mean should be of order 1. And the martingale term, it's the same as add a bunch of Gaussian, you get the extra 1 over square root n. So the martingale term after n steps, they accumulate to give you a Gaussian fluctuation of order 1 over n. And you can think this is a discrete stochastic equation. So you can take some limits, you will get a continuous stochastic differential equation. So this will give us a very good analysis for non-intersecting Bernoulli random walk in this form. Now, in this way, we can analyze this line intersecting.
Can you maybe say a little bit more, like how does the, because you have expectations, how does it become a stochastic differential equation?
Oh, as you can see, usually you have mt minus mt plus 1. Because of this is the transition probability, the difference always has a deterministic at the martingale term. Essentially here, I mean, you can use this loop equation to compute this deterministic term precisely, and also the covariance structure for the martingale term.
Okay, okay.
Yeah.
Thank you.
So in this way, we can solve for the correction term by the Feynman-Katz formula ETX using this non-intersecting Bernoulli random walk. And it turns out the quantity we are interested in, so ET plus 1 over n over ET, this term is split. The leading term is E to the sum over EI over n ft at xi. So because of this split, so you plug in, so our non-intersecting Bernoulli random walk, it corresponds to the random Lorentz tiling. The transition probability is this one times this one. So you can absorb this ftxi back into gtxi. Then you get this non-intersecting random walk. The transition probability is roughly given by this guy. The only difference from this one is here is gt, here is gt tilde, which is just gt times plus this correction, smaller order correction term ft. And because they are of the same form, so you can also analyze it, just use the dynamic loop equation and get the Stieltjes transform converge to some stochastic differential equation. And you can also think the Gaussian free field, cut it into slices, and also write down, view it as a Markov process, and also write down the stochastic differential equation. Turns out they are the same object. Then we can conclude this non-intersecting Bernoulli random walk corresponding to the random Lorentz tiling converges to the Gaussian free field. So maybe let me just quickly wrap up. Just explain why we need to assume it only have one upper boundary edge. It's because if there are two upper boundary edge like this guy, the liquid region is in the shape something like this. As you can see, something happens at this point at this time t. It turns out at this time t, the drift term is not analytic. It has a branch point at this point. So as you can see, for the loop equation, the analysis of it somehow heavily depends on those kind of analyticity. To analyze something which is not analytic, which has a singularity, it's much harder. And the boundary condition I choose, like you only have one upper boundary edge. It's just to make sure all the cusp is like something like this. It's facing upwards. There's no cusp facing downward. So that's the real condition. Let me quickly summarize. So in this week, we proved the fluctuation of a height function for random Lorentz tiling with exactly one horizontal upper boundary edge. I show it converges to the Gaussian free field. And important too is the dynamical loop equation. And for general domain, if you want to do it for general domain, then you need to analyze this dynamic loop equation for this phi, which has a singular. Hope I have more to say about this in the future. Yeah, I think I can stop here.
Okay, let's all thank Jay.